Okay. So today, what I have on tap is one more thing. I will not be having office hour from 10 to 2 today. I have to take off. If you're planning to meet with me, just come talk to me. So I will be, but not till this afternoon. So. So I'm going to put these examples in the notes. I was going to write some stuff this morning, but I got kind of too busy. But I did write up some stuff last night. I think this will be kind of fun. So I want to look at prime decomposition. And mentioned two quadratic points. So I'm going to kind of base my example on this. I want to show how things decompose and operate. Number of fields. The last time we talked about the following result. About the following result for quadratic fields, and I'm pretty sure I'm going to ask you all do this. If D is a square for integer, then degree Q radical D over Q is equal to 2. All right. And its ring of integers is given by number 1 or as I pointed out last time, it's really easy to see that everything in here is integral, right? I mean, you can explicitly write down polynomial. Let me look at this one here. I'll do kind of a quick computation. In the second case right here, if you have A plus B times 1 plus radical over 2, where A and B are integers and D is equivalent to 1 by 4, I will reverse engineer its minimal polynomial. If you would multiply this out, what happens when you add these two coefficients? If you add these two things up, its negative sign should be coefficient of x. And what do I get? Well, I get 2 A's, and notice that this conjugate here, it cancels the radical term. And so I get 2A plus B, I guess it is. That look right to y'all? And then the last thing I do is I just multiply straight up, multiply this out, and I get a squared. And then I get two AB times this product, right, so I get two AB times the sum of these two, which is just going to be two AB, isn't it? AB, right, AB half, so this is AB. And then I get the last part of it, B squared times the product of these two, whatever that turns out to be. And the product of these two is actually 1 times D over 4. So that's what I get for sort of minimal polynomial of this. And look what happens here. This looks like it's a rational number, but D is equivalent to 1 minus 4. So 1 minus D is actually 4 times an integer. So this last hanging thing is actually an integer. So that's sort of why this works. Now, the big fat question for the day is why is this everything, right? And there's a couple things to worry about. So it is true. So let me also point out that. So everybody see why this is an integral polynomial. Let me also point out here, it's certainly the case. A minimal polynomial radically is x squared minus d, right? And as long as it's square free, that radical d is in fact not a rational number, right? That goes back to brother Pythagoras and all that kind of thing. But the next question is why any quadratic extension? Well, suppose now quadratic polynomial with this generally, you might pick on me a little bit for saying this is mine, but if it's truly a quadratic, I can get rid of it. It's a leading term. It'll have the same roots, right? So notice this is a little embarrassing, but this is equal to x minus a over 2 squared plus b minus a squared over 4, isn't it? Actually, probably plus, wouldn't it? Everybody agree with me? And so the point is notice that, of course, the solution to this at the end of the day is the following. Of this when it's all said and done is negative a plus or minus the square root of a squared minus 4b over 2. So this is an arbitrary quadratic polynomial with coefficients of rationals, right? Now, when does this give you something interesting? Well, notice a, 2, these are all rational numbers. This is a proper extension. If and only if a squared minus 4b is not a squared. Yeah. right? And notice that getting one root is the same as getting the other. It doesn't matter which sign it is, because if you've got one, all you gotta do is change the sign and multiply this or add a certain number to this, you get the other one. Right? Okay. So this is actually something that is peculiar to quadratic, right? Because even for cubics, just having one root in the extension does not mean that you have all the rest of them, right? In fact, just take q adjoint with the cube root of 2. You got the real cube root of 2, but you don't have the two complex conjugate ones. They're not written. And we can assume that A equals and B equals K over N, where N and K are integers, and N is not 0, of course. And so this thing right here is squared. This is M squared. Yeah, that's what I'm trying to do here. This is M squared minus 4KN. And so really, the extension we're getting here if alpha is the root of the original, then Q adjoined with alpha is the same as Q adjoined with the square root of M squared minus 4KN. Right. So notice that we can write notice that whatever this integer is, I don't care what it is, I can factor it into primes, right? Well, as long as it's not 1 or -1, right? Or 0. But of course, if it's 0, then that means that this is just Q in the first place, right? If it's 1, it means it's Q in the first place. But even if it's -1, then I can certainly pull out 1 and leave you with D the square for me, right? So Q alpha is equal to Q adjoint with radical T squared D, which is Q adjoint with radical D. Again, I can pull T squared out. So quadratics are very nice because you can always write them in that form, right? And like I said, cubic extensions there's a cubic extension, but they don't all look like this because I might have Q alpha, where alpha is root of x cubed minus 2x plus 2. All right, and good luck writing that. You can't write that as a pure cubic. Okay, but again, let me go back to the problem at hand. So everything in a quadratic extension is the root of some quadratic polynomial, right? The ring of integers are looks like one of these two, So there's a couple things. We've sort of verified that everything in here is root of some money. Oh, no. Here's the thing that may bother me a little bit, and that is, why is there not more than what we've listed here? Right? How do I know that there aren't some other fractions in here that satisfy some polynomial, root of some polynomial? And here's another question. How do I know for sure that my monic polynomial has to be quadratic? Right? It is true that everything in this field, and hence in this ring, is the root of a quadratic polynomial with coefficients in the rationals. Right? But how do I know that I can't make, how do I know that there's not something in here that satisfies a quadratic polynomial over the rationals, right? And that's its most efficient one. But then it also is a root of a monic polynomial, say of degree 5, right? So you've got this monic polynomial of degree 5. This does satisfy a polynomial of degree 2, but not a monic one, but there is a monic polynomial of degree 5. How do you know? It's not true, but see if you can figure out what's true. But for right now, let's just take rings of integers here. Like I said, I wanted to discuss decomposition, and a good place to start. And as I promised, is connect to quadratic forms. Let's start with I'm going to do a number of examples, probably this day, probably it might bleed into the next day. And I hope to use this to bootstrap some theorems. I'm going to generalize my examples. So I hope this will be kind of fun. So you guys are going to help me do some computations. So let me ask you this. How many are familiar with this? You might have seen this in number theory class. You might have seen it in algebra 2. How many of you seen it? Actually, maybe even graduate algebra 1 or undergraduate. How many of you seen the norm function where you multiply by the conjugate? All right. In bigger fields than this, it's a little bit more complicated, but not much. This is the norm. Okay. And in fact, not only is this kind of a neat number theoretic thing, this is actually a Euclidean norm. You can consider this as sort of a measure of the size of this element, and actually you use this to make a Euclidean domain. You might remember the properties. Norm of alpha is 0. If and only if alpha is 0. 2, norm of alpha beta is and 3. You better remember what the other one was. Plus or minus 1. Right. Norm of alpha is just 1 for this one, right? But more generally, it can be minus 1. Say R, so I can say more general. The norm's multiplicative. By the way, this is let me just show you this one. And this actually kind of shows you the power of this sort of thing. Let alpha equal x plus iy, beta equal a plus ib. All right. let's see, this is ax minus yb plus I times xb plus ay. Yeah, this is already looking rather depressing, right? So what is the norm of this blob? This is ax minus yb squared plus xb plus ay squared, which is a squared x squared minus 2axyb plus y squared b squared plus x squared b squared plus 2abxy plus a squared y squared. Right. Okay with that? How about that? Like I'm in a trig class. And this is a squared times x squared plus y squared. And I guess we'll have b squared times x squared plus y squared as well. Which is a squared plus b squared, x squared plus y squared, which is the norm of beta alpha. Last step, the integers are commutative, so beta, right? That's just for this one form, right? That really nobody wants to do this in general. Oh, I prove this for me again, easier.
Use the determinant definition of the norm. It's like multiplication by alpha induces a linear map, and you take the determinant of the matrix that corresponds to it. And
yeah, maybe my parents were cousins, though. I'm gonna do something.
That's a Gaussian extension.
Norm of alpha beta is alpha beta. It's conjugate, right? And complex conjugation. Use the Galois theory. More generally, you can do this Galois. So the norm is a very this holds for any norm. I'm going to just do norm for quadratic fields right now. Now let me sort of use this. The norm's going to come up quite a bit here. So the norm of x plus y such as y squared. Now, what I want to do is the extension is generated over Q, and in fact over Z in this case, and we restrict the integer by I, which is a root of x squared plus 1. Right. So I can sort of consider really this ring is what I get when I take Z and I stick on a root of this irreducible polynomial. Right? Now, consider a prime. Z 0. Now let's see what happens. What happens to this generating polynomial when you look at it over a prime? Well, The answer is it depends. In Z mod 3, x squared plus 1 is irreducible. I really dig quadratics and cubics for that matter too, because to test for irreducibility, all you gotta do is see if it's got a root or not, right? Because either it's stuck as it is, or it has to have a root. And if you look mod 3, plug in 0, and you get 1, plug in 1, you get 2, which is -1, not 0, and plug in -1, and you also get 2. No roots, irreducible. In Z5, squared plus 1 is x squared minus 4, which is x plus 2, x minus 2. Well, I could keep going with primes, next one's 7, and so forth and so on. But I see one of two things can happen, mod P. Either you're stuck or you break down, right? Now, anybody want to predict pattern to this?
It'll be a -1 to the square.
That's exactly right. Right? When does this break down? Precisely, it breaks down if -1 is a square mod, whatever. In terms of what we've learned this semester, in ZP, P factors, or I'm sorry, x squared plus 1 factors, non-trivial. If and only if -1 is a square. Mod. If and only if simple -1 P is 1. If and only if P is equivalent to 1 mod 4. Problems, I really should say odd P. Because mod 2 -1 is a square because it's the same. But our Legendre symbol doesn't really cover equals 2. So this is kind of nice because what it means is for mod P, when P is equivalent to 1 mod, so we'll ignore 2 for a moment. If P is odd, then if P is equivalent to -1, then or if P is equivalent to 1 mod 4, then -1 is a square, and you get that polynomial breaks down. If, on the other hand, P is equivalent to 3 mod 4, you're stuck. What does this mean for ZI? Well, and I'm going to use the fact that, no, I will do this first, this example, the next one. ZI is a UFD. I'm sure you all have all encountered this, we've mentioned it, of course, it's Euclidean domain. Well, what this means is, if P is odd and P is equivalent to 3 mod 4, then P is prime. not only in its original ring, but it's also prime in ZI. Because it's if P is equal to 1 mod 4, P flattens into two distinct primes. This. And I'm going to go through this using a normal. So first, P is equivalent to 3 mod. We'll see what happens. Suppose that P breaks down into smaller chunks, right? Apply the norm. Now, the norm of P, just using our formula, is, well, this is P plus 0I, so it's P squared. So what this means is P squared should be the norm of alpha times the norm of beta. If the norm of alpha or beta, either one, is 1, that means my factorization here is trivial, right? I agree with that. So only way alpha and beta are non-units is if norm alpha is equal to P. Everybody agree? So the only way that P can break down is if these two elements both have norm P. That's the only way to do it. Norm is very useful. Well, we'll see what happens. So let's suppose, just for giggles, that that means that A squared plus B squared is P. Right? Or in other words, I could say in other words, therefore, A squared plus B squared is equal to 0 on P, right? Notice that neither A nor B, as a matter of fact, can be equivalent to 0 mod P. What's the problem? Let's suppose just for giggles that B is equivalent to 0 mod P. What happens then? The other half also is. So they will both have to be. Everybody agree with that? So if B is equivalent to 0 mod P, that forces A to be equivalent to 0 mod P. That means that both A and B have a factor of P in it, right? So in other words, P divides alpha, And now the norm's too big, because that would mean that alpha would have to have a norm of at least p squared or bigger. Everybody agree with that? So this can't happen. They're both units mod p. So since, for example, p is a unit mod p, I mean, this field divide out by it. Because p is equivalent to 3 minus. So you can't have minus 1 being squared. So this justifies this statement right here. I'm been dying to try this one. Let's see. So really what we've shown here is that if P is equivalent to 3 mod 4, then P is irreducible and hence prime, because it's a UFD, in the Gaussian integers. Everybody okay with that? What about the other case? Well, now let's suppose P is equivalent to 1 mod 4. So now all the primes like 3, 7, 11, these things in the Gaussian integers all remain prime. Right? What happens if P is equivalent to what happens in this case? Well, notice that so I'm going to claim now that in this case, C yeah. Okay. Any ideas on how we're going to do that?
Are we allowed to use the fact that it's a prime with the sum of two squares?
Well, actually, I was kind of hoping to come back the other direction, yeah, but I mean, that's right. It is true that any such prime, so let me jump on his idea. So the classical thing is if P is equivalent to 1 mod 4, then P is x squared plus y squared. Right. And notice that this is the norm of some alpha. Where alpha equals x plus y. And what this means in this case, is that P is equal to x plus y times x minus y. Right. And notice that the norm, actually the one of them, is P. So these are prime, or well, are irreducible. because its norm is P, so if it's got a proper divisor, its proper divisor must divide P. Its norm must divide P, I should say. And so any proper divisor has that for norm one, that doesn't count as a unit, or norm P, but that doesn't count because it means the other one has to be. So these are both. But can anybody think how we might could do this more or less from first principles?
Could just follow through the same pattern that you did for, E is equivalent to 3 mod 4.
Okay, well, one of the things you could do is, since P is equal to 1 mod 4, there is a solution to, everybody okay? So multiplying, so in particular, so, so now you can assume, well, of course, that it's convenient that we have one here. If what happens if P and K are relatively prime? So let me point out that in the Gaussian integers, this is x plus I, x minus I. Right.
On the left hand side, square, on the right hand side, next one back.
Right, so. Here's the first question is, can P be prime? If you look at this, actually, I don't even think I need this right here. It's certainly true that P divides the product of these two. Right? But notice that P doesn't divide either one. Right, because in particular, the coefficient of I is 1, -1. So it doesn't divide equal 1. Now, again, I'm going back to the CI as UFD. What does that mean about P? So here, there's a factorization technique, so I am following the title of the class. P divides its product, but doesn't divide either one. That means the P is not prime. Right? It can't be, because it divides the product without dividing either thing in it, right? Therefore, P is not irreducible. Because ZI is a unit of P. So again, I don't feel too bad about leaning on that because I've already leaned on it before. So if P is not prime, and I know it's a U of P, that means P can't be irreducible. So that means that P must break down, right? So P must be alpha beta for alpha beta in ZI non-units. Because it has to reduce in a non-trivial way. Use the norm again. Norm of P is norm of alpha, norm of beta. Has to be. And this is P squared. Since these are irreducible, this implies the norm of alpha must be P. Right? Because it can't be one and it can't be P squared, because I'm assuming that this is an honest to goodness, old fashioned American factorization that's non-trivial, right? If alpha is A plus BI, then this equation here gives alpha plus BI, alpha minus BI is equal to P, or A squared plus B squared. So now that we know that ZI, now we've come full circle and got that any prime equivalent to 1 mod 4 must be a product, must be, I'm sorry, a sum of 2 squares, right? Which is kind of interesting. So what do we have? Well, so in ZI, we have the following behavior. P is equivalent to 3 mod. That's what happens here. P is equivalent to 1 mod. Then P is equal to A plus BI, A minus BI. It is the product of 2 primes, both are norm true. And 2 is similar to this, but it's a little bit different. 2, it's its own box. It is 1 plus I squared minus. So it's, I think I got that right. That's going to be, whoops, not quite. There we go. This is a unit times a square. 2 actually is 2. These factor into 2 distinct primes. 2 is degenerate. Sometimes we'll call this ramified. It is actually a unit times a perfect square. So the 2 primes here are not distinct. So here is a question to kind of tickle your brain, because for next time, let me ask you kind of a parallel question. This was the UFP as well. Which primes can be written P equals x squared plus 2x. Which primes can be written in this prime? And you can use the fact that that thing is also. So think about that. We'll do some more examples and then I'm gonna bootstrap up to a more general case and show you how to do it. Actually, I'm gonna do one after this. It's not a UFD and that's when it starts getting really fun and obnoxious. Okay, any questions? Yes, sir.
This might be like a far-reaching thing, but one. The ramification. You know what I mean, or talk to geometric correspondence with that, and like.
Yeah.
Like sheets top on top of each other, type
There-
of thing.
There's something like that. And actually, it turns out that in general, for extensions over Z,
Yeah.
you always have some primes that are ramified that behave like powers in a certain sense. That's really fast and loose, but it behaves sort of like powers, but there's only finitely many of them. Right? In this case, there's only one, and in general, there's only five. And I'll show you actually how to figure out which ones they are. So, other questions? Yes.
Is there a nice characterization for like cubic rings of integers, like say Galois cubics, so like they're like not like cube root 2, but like.
Right, so, yeah, there are different kinds of cubics. There's pure cubics and there's different sort of types of cubics. And there's certainly some work that's been done, but nice, certainly not as nice as this. And nothing comes to mind that I really know of. Okay, others? All right, you all have a great weekend. Think about the math club, and we will see you on Monday.